Welcome back to this course on computational thermodynamics and kinetics of materials. There are many methods to make phase diagram experimentally. One method we are going to focus on in this class is called cooling curve method. So we'll plot two types of phase diagrams, isomorphous phase diagram and eutectic phase diagram, and then we'll see how a deviation from the phase diagram will happen if we use this method. The equilibrium phase diagram is supposed to be an equilibrium one. If you use this method, you will see that there is some kind of a non-equilibrium creeping in. Okay, that can cause such some deviations. We will see about that also in this class. Okay. So this is a non-isothermal method. Non-isothermal in the sense that we are not going to keep things at one temperature for a long time, which is supposed to be the equilibration treatment method, but we are not going to do that here. We are going to use something called a cooling curve in this method. Okay, what is a cooling curve? It's a temperature versus time plot. It's going to be, let's say, the composition is represented here, meaning for a selected composition, we are going to plot temperature versus time graph, and it's going to, and it may look like this: the liquid's temperature coming down, and at a particular temperature, the curve changes, becomes something else. Then again, it goes down with a different slope. So you can see that there is a continuous slope change. Okay. So this region can be labeled as liquid and this region solid. This is basically a solidification tracked by cooling curve method. So temperature versus time graph. So how to make this diagram? Cool from liquid state and note variation in temperature against time. And then repeat it for various compositions. Once it is done, translate the information that we got from this cooling curve, translate the transformation temperature and composition information to another graph. So we have the composition information here, and we see that there are some changes happening here. These points of change can be translated to another graph of temperature versus composition, where which will eventually be the phase diagram. Let's see how to do that. So this is a AB system, and we have multiple compositions of AB, starting with the pure A, and then increasing the amount of B slightly, and then increasing the amount of B equally 20, 40, 60, 80, eventually reaching pure B. Right? This is the kind of compositions we have. So 6 compositions in a binary system. It's a very small set of compositions to start with. So this is the temperature versus time plot. So let's say liquid is stable for a temperature range, and then it changes to solid, and the solid cools down. Okay, this is basically how the material cools down. When the material cools, what we have to keep in mind is that, you see, the heat extraction is happening at a constant rate. The amount of heat taken out per unit time is kind of constant. If that is the case, then the temperature should be falling gradually, right? But that is not going to happen. You will be seeing the regions like this where the temperature is not at all falling, but the time is increasing. But remember that heat is extracted out. So this is what happens when things are exothermic in nature. The transformations, when they are exothermic, the heat is coming out of the reaction or the transformation, and that holds the temperature. This kind of things happen. Right. So this is how the liquid cools to solid state. Now this is the solid. These 2 points here, if we note, this is where the changes happen, and translate those 2 points against this composition. So 100A 0B is there in this plot. This is the phase diagram. So we can see that 0B and 100A point is here, meaning pure A point is here. So at this composition, these 2 temperature points should come, right? So let's translate them here. So they indicate that liquid to solid happens at this temperature. That's the point of this, right? Then we'll go to slightly higher amount of B. What happens here? So the liquid to solid transformation happens, but not at a single temperature, but over a range of temperature. At this temperature it starts, at this temperature it ends. Okay. Translate this against 2080. Okay. So this is the 2080 composition. This is the temperature at which the liquid starts to transform to solid, and this is the temperature at which it ends. Okay. Then you have this one more line where you have two more points like this. Translate them here and repeat for all the compositions. Right. So now what you got is the temperatures at which liquid started to transform to solid and the temperature at which the complete solid has formed. So join these lines. This is the liquidous line. Above that, entire things are liquid. All the compositions are liquid. And this is the solidus line below which everything is solid. In this case, it is a solid solution alpha. And between them, liquid plus solid is going to be stable. Right. So now you got a isomorphous phase diagram from cooling curve method. Now how to get something like this, an eutectic diagram? Let's see that at least one half of the eutectic will try to do this. The other half is going to be similar. Let's start with this 0% B and 100% A. Liquid cools down, it's a pure metal. The solidification occurs at one single temperature. So this is straightforward. And then for 595, 5B, 95A, the solidification is going to be like this. And let's translate these points also here. So only so liquid to solid points I am taking it here, but you can see there is a small slope change here also. In the solid state there is a transformation. For the simplicity sake I am avoiding it. So if you see here, this is the composition where the eutectic point may cross. Okay, this is the pro-eutectic phase formation region. Then this is the eutectic transformation region, which will be like a horizontal line. So let's translate these points here. Then things are going to happen at one single temperature as if it is a pure metal. We have seen this idea before. So this is how the eutectic point will look. Joining these lines, we will get liquidus and solidus, and this is a eutectic reaction line. Below that it will be alpha plus beta, above that alpha plus liquid, and this is the alpha region encompassed within the solvus lines. So these points come from the cooling curve method, and this can be repeated to the right hand side also, and a eutectic diagram can be obtained. So we also talked about this in one of the previous classes. So as we cool, the microstructure microstructure can be quite different at high temperature, complete liquid and liquid plus solid plus and at a lower temperature it can be completely solid. More importantly, this is not just continuous cooling. Okay, we say phase diagrams does not show what happens during cooling. It is essentially it shows what happens when the materials attain equilibrium at each temperature. Meaning at every temperature it has to be exposed for a really long time. Then what are the phases inside? Okay, that amount of phases, composition of phases should not change with respect to time further. That's the meaning of attaining equilibrium. Once that happens, what we see in the microstructure will be reflected in the phase diagram. So that's the meaning of equilibrium phase diagram. But here in these cases, we are talking about cooling and then what happens during cooling and all, which is not strictly right. So we can say when extreme slow cooling occurs, this may be true. At least at high temperatures, this can be true. Since we have used the cooling rate method, there should be some deviations in the phase diagram compared to the equilibrium phase diagram. Let's see one example for that. This is through thermal analysis, which is nothing but the other word for cooling curve method. Okay, so in that a tin by bismuth system is analyzed, and these are the cooling curves. And graph showing temperature of several tin bismuth alloys cooling over a period of time, lines displaced along the time axis. We have done that previously in terms of composition. We kept different compositions here. So here in the time axis, they are all displaced slightly. It doesn't matter. You get the point. This is about the cooling curves for different compositions. The compositions are given here. The color coded, the colors are indicated here. The dark red here is this 0% bismuth, and as the bismuth content increases, you see all these different colors appearing. So this is the cooling curve for a tin bismuth system. If these are translated to phase diagram, it's going to look like this. So this is this white line here is the one obtained from this cooling curve method, and if you see carefully, there is a gray color phase diagram here. Okay, there is a gray color line. Okay, that is looking almost similar but deviated. Okay, so the white line, it is from the cooling curves, and the gray line from many experiments over long time. You see, even equilibrium isothermal techniques are there. We will talk about them later. So those techniques will give us a more accurate phase diagram like this. So that will be slightly deviated from what we get from the cooling curve. So the cooling curve method, if it is reported, if a phase diagram is reported to have been drawn by cooling curve method, you have to keep this in mind that it need not reflect the actual equilibrium diagram accurately. Thank you. We'll see in the next class. We'll start with thermodynamics and continue in the next class. Thank you.